Deploying a Ruby on Rails application has never been easier. Thanks to platforms like Heroku, Render, and AWS Elastic Beanstalk, you can push your code to their service and have it handle all the complexities behind the scenes. However, the convenience of using these platforms comes at a price. Often, you need to pay separately for all the moving parts in your application. For example, a typical Rails application will need a database, a worker service to process asynchronous jobs, additional data source for search and caching, and so on. Throw in load balancers for high availability, and you'll see how quickly the cost can rack up. Now, you can argue that this is still cheaper than paying for an additional employee or freelancer, and in many cases, that's a correct assessment. However, for small startups that operate on a shoestring budget while trying to expand rapidly, these costs are not uncommon to spiral out of control as the company grows. You also need to worry about vendor lock-in, which can make migrating out of your existing provider painful and expensive. Is there an alternative that can help you deploy production Ruby on Rails applications that is as simple as pushing code to Heroku while giving you the freedom to choose your preferred infrastructure at any given time? That's where Kamal enters the picture. Kamal is a tool that allows developers to deploy containerized web applications without worrying about the underlying infrastructure. It can also set up and manage web applications using your preferred infrastructure. It doesn't care if you use servers from DigitalOcean, AWS, or even a bare metal server co-located on a physical rack. You can deploy your web apps in minutes as long as you have access to a server through SSH, and your web application can run on a Docker container. While Kamal works great for deploying web applications, we still need a server to deploy to. These days, it's super easy to spin up a server on the cloud and have it available in under a minute. You can do that by logging into your cloud provider, but a more effective approach is to manage your servers through code. This way, you can ensure your environment is trackable and reproducible, making it easier to maintain and scale down the road. My preferred infrastructure as code tool is Terraform. Terraform allows you to define your servers through a configuration file. Like Kamal, Terraform is platform agnostic, so you can build and manage your infrastructure with your choice of provider. In this video, I'll show you how easy it is to create a new server on the cloud using Terraform and use that newly created server to deploy a Ruby on Rails application using Kamal. Let's jump right in. For this screencast, I'll go through the process of creating a new virtual private server using Terraform and deploy a Rails application on it using Kamal. Before diving in, let's go through some of the prerequisites needed to do this. On your local system, you need to install Terraform and Docker. My environment already has the latest versions of these, so I won't go through the installation process. But if you follow along with this video, make sure you have them set up on your system. I'll share some links in the video description to point you to their installation instructions. Next, you need a web application that has a Docker file ready for deployment. I'll use the Airport Gap application that I have shown previously on this channel, since it already has a Docker file that works. This is a Ruby on Rails application, but Kamal can work with any web app as long as it has a working Docker file. Finally, you need access to a service that allows you to spin up servers on the cloud. For this video, I'll use Hetzner Cloud as my provider, but you can use any similar service like DigitalOcean or AWS. Since we need to create a server first, let's go through the process of setting up our Hetzner Cloud account to use with Terraform and Kamal. I'll need to add my system's public SSH key so we can easily access any new servers we spin up. I'll also need to generate an API key to allow me to create any resource on my Hetzner Cloud account through Terraform. To do this, I'll go to my project on Hetzner Cloud, go to the security section, and in the SSH key section here, I'll click on Add SSH Key. This will pop up a modal asking for the public SSH key and the name. I'll copy and paste my key here and give it a descriptive name. After copying my SSH key, you can also set this as the default key. I won't set it up as the default key because I prefer to choose which SSH keys to use when creating new servers, but you can decide to use your system's key as a default for convenience. After adding my SSH key, I'll go to the API token section and generate a new API token. We'll give it a description and make sure that it has read and write permissions, since we'll use this token to create new resources. Once you click on Generate API Key, it's very important to get this API token and store it in a secure location now, because you won't be able to access it again once you close this module. With these two steps, our Hetzner Cloud account is now ready to use with Terraform. For purposes of this demonstration, I'm going to use a separate directory to hold my Terraform code, but depending on your team, you might want this as part of your application code repository. I'm starting with an empty project here, so the first thing I want to do is create a main Terraform configuration file called main.tf. The name of this file follows standard naming conventions for Terraform and is considered the root module. More complex projects will use additional modules, but we won't cover that here. A Terraform project starts off with a provider, which are plugins to interact with other services through their APIs. It allows Terraform to communicate with different providers using a standard configuration. You'll find Terraform providers for almost any cloud service out there. Here, we'll use the Hetzner Cloud provider. In the documentation for this provider, we can see some examples on how to set it up and how to put it to use. First, we need to start with the Terraform block to tell Terraform which providers we're going to use. We'll also specify which version of the provider we want to use, so anyone else using this Terraform configuration will have the same version to prevent any surprises. We can get this information by clicking on the Use Provider button on the documentation, which gives us the details on setting it up. We'll copy and paste this Terraform block and place it in our main.tf file. We'll also need to configure the provider to connect our account. We'll do that using this provider block in the Terraform configuration. Now, the options used here depend on which provider you use. The documentation will have an argument reference section to explain how to configure this provider. As we see here, the token argument is required, which is the Hetzner Cloud API token that we generated earlier. We can also use an environment variable, but it's better to set this up into configuration so others know how to configure things on their own systems if they were to use this file. Since the token is a sensitive piece of information, we won't want to place it in plain text here. Instead, we'll set it up as a variable so each contributor to the project can set it up on their systems. Inside the provider block, we'll add the token argument and set the value as a variable called Hetzner Cloud API token. The var syntax tells Terraform that this is a variable, and we'll need to declare it in our configuration. We can do it in this file, but it's common to place these in a separate file called variables.tf. After creating the file in the project, we can declare the variable using the variable block. This block requires a label, which is the name of our variable. Hetzner Cloud API token. Inside the block, we'll set a few arguments. These are all optional, but it's a good practice to set some of these for security and maintainability. The first argument is sensitive, which tells Terraform that this contains a value that shouldn't be shown in Terraform's output. It's a Boolean argument, so we'll set this to true. The next argument we'll use here is the type to indicate the value type this variable can accept. The API token is a string, so we use that here. If we don't specify this type argument, Terraform will accept any data type. In this simple example, it's not an issue, but for more complex Terraform configurations, setting the type is a necessity. The last argument we'll use here is the description, which serves as documentation to tell others about this variable. Again, for this simple example, it's not needed, but you should get into the habit of creating descriptions here to make it easier for others and yourself down the road. With this variable declared, we need to set the value somewhere. Terraform has a couple ways of doing this. For example, you can use a command line option to pass the value, or you can run Terraform with special environment variables that Terraform can pick up. In this case, I'm going to create a separate file that uses these details. My preference for smaller projects like this is to create a separate file. Terraform can automatically load a file named terraform.tf vars, which makes it convenient to set these variables. This file uses the same syntax as setting arguments in Terraform, so all we need to do is add the name of our declared variable, in this case Hetzner Cloud API token, and set the secret value. Given that we don't want to expose our API token, we should inject this file into a remote code repository, so make sure to add it to your gitignore file or similar for your preferred version control system. Now that we have our Hetzner Cloud provider configured, let's initialize the Terraform project by using Terraform init. I'll switch to a terminal and run the command Terraform init. So this command downloads any providers we specified and sets up the initial state of the project. After a couple seconds, we'll see this message saying that we're ready to use Terraform. With the project initialized, let's go back to our main TF file to continue setting up our infrastructure. The next step is to begin creating resources. We'll want to create a server, but before that, we'll need to set up a couple of additional resources first. First, we'll want to begin securing our server by setting up a firewall that allows only web and SSH traffic to our servers. Hetzner Cloud offers its own firewall service that we can associate to any of our servers. We'll set one up now using Terraform. To manage a resource with Terraform, we'll use the resource block. This block uses two labels. The first one is to indicate the resource type. In this case, a Hetzner Cloud firewall. The second label is a local name to describe this resource and use it as a reference in the configuration. Going back to the provider documentation, we need to figure out which resource type we need. On the left of the documentation, we can filter out the resources, so let's search by firewall. We have a couple resources and data sources related to firewalls. The one we're interested in is the hcloud firewall resource type. As shown here, this resource lets us set up a firewall in our Hetzner Cloud account. Going back to our Terraform configuration, I'll begin configuring this resource. I'll create a new resource block with the type of hcloud firewall, and I'll name it web server and SSH as its identifier. Let's go back to the documentation to see which parameters are required and which ones we want to include for this resource. As we see in the argument reference, there's no required arguments, but we want to set a couple of these. I want to set a name for this firewall to help me identify it on the Hetzner Cloud console. That's done using the name argument. I'll use the name argument and call this firewall web server and SSH. I also want to add a few rules to tell the firewall what kind of traffic I want to allow. That's done with the rule argument, which is a block itself containing additional configuration as shown below it. Some of these options are required when setting a rule, like the direction, the protocol, the port, and the source IPs. So we need to make sure to include those. I'll also include the description to document what this rule does. For our first rule, I'll set it up to allow traffic on port 80, which is for non-secure HTTP traffic. I'll set the description as allow HTTP traffic. Next, I'll set the direction, which defines whether this rule is to allow inbound traffic to the server or outbound traffic from it. This rule is to allow traffic into the server, so we'll set this value to in. Next, we need to specify the protocol for this rule. Since it's for web server traffic, this value should be TCP. For the port, we want to set it to allow access to port 80. Finally, we need to specify the source IPs for this rule. Since this is a rule to allow public inbound traffic, we need to tell the firewall that we want to allow access to all IPs, which can be defined with 0.0.0.0. Note that the value for source IPs is a list, so we need to set this IP inside these square brackets. It also needs a subnet, so we'll specify the subnet as 0. In addition to this IP address, later when we set up the cloud server, we'll set it up using both IPv4 and IPv6 enabled. So we'll also want to allow all IPv6 traffic in this rule. The IPv6 equivalent of 0.0.0.0 is :/0, which we'll add to the source IPs list here. This configuration sets up our rule for HTTP traffic. Let's copy this rule and do the same for HTTPS and SSH traffic, which only requires changing the description and the port. Everything else remains the same. With this, we should now be able to manage our Hetzner Cloud firewall through Terraform. Let's check that everything is working before adding new resources. In the terminal, I'll run the Terraform plan command to check that our configuration is working. As we can see here, we have a couple errors. If we read the error, it says invalid number literal, which means we did not set these as strings. So let's go back and fix that issue. After fixing those strings and rerunning Terraform plan again, we can see that Terraform created an execution plan, which shows you what changes Terraform will make when applying them against our current infrastructure. Running this command is a good safeguard to ensure we don't mess up our existing infrastructure. Since we don't have anything in our current state for this Terraform project, Terraform will tell us that it's going to create a brand new firewall based on our configuration. This output looks okay, so let's go ahead and apply it on our Hetzner Cloud account. I'll run the Terraform apply command, which shows the execution plan once again, but this time it asks if we want to apply it to our account. So I'll enter yes here and proceed. After a few seconds, we'll see that the operation completed successfully and our firewall was created on Hetzner Cloud. If we go back to the Hetzner Cloud account and go to the firewall section, we'll see our new firewall fully configured. With the firewall set up, let's move on to our next resource. We can jump into creating a new cloud server with this, but before that, I also want to create a private network to use on our server. While this is an optional step, the reason I want to do this is because Kamal exposes any services we define, like the database, through a public IP address. I don't want to have those services exposed to the public, so creating a private network is the way to secure them while keeping them accessible within the environment. Hetzner Cloud also gives us the ability to create private networks that are closed off to the internet, and we can also manage those through Terraform. If we go back to the Terraform provider documentation and filter resources by network, we'll see the hcloud network type. This resource sets up a network that we can use later in our server configuration. Let's begin managing this resource in our Terraform configuration by adding a new resource block with the hcloud network resource type and an identifier called airport gap private network. Looking at the documentation, we can see that there are two required arguments for this resource block, a name and an IP range for the network. For the name, let's call this airport gap private network. As for the IP range, I'll set this up using the prefix 10.0.0.0 with a subnet of 16, which is just for demonstration purposes. It's a little bit overkill because we're only going to use it to set up one server, but for now we'll just keep it at this subnet. This defines our network, but we also need to define a subnet to allocate IP addresses from this private network. Terraform has another resource type called network subnet to manage this. This resource type requires a few arguments like the type, the network ID, the network zone, and IP range again. I'll go through each of these as I set them up in our Terraform configuration. We'll create another resource block here using the resource type hcloud network subnet and identify it with airport gap private network subnet. The first argument we'll use here is the type. Hetzner Cloud offers a few network types, but since we're going to use this on a cloud server, we'll set this value to cloud. Next, I'll set up the network ID. The value here should be the ID from our created network. We don't have that ID right now, but the cool thing about Terraform is that it allows you to reference attributes from other generated resources without us needing to specify it explicitly in this configuration. To get the ID associated with the network we're managing in this Terraform configuration, we'll use a dot separated reference consisting of the resource type, which is hcloud network, then the identifier we want from our configuration, which is airport gap private network. I just noticed there's a plus sign here, it should be an underscore. Finally, we'll need the ID of this network. If we go back to the documentation for the hcloud network resource type, it'll have an attributes reference section detailing what attributes Terraform will have for a managed resource. We can see here that we can get the ID using this ID attribute. So let's go back to our configuration and add it to our reference. This handles setting up the value of the network ID. We still have a few more arguments to define for this resource. The next argument we want to define for this resource is the network zone. The zone of our network subnet will depend on the location of the servers that will use this private network. For this example, we're going to create the server on Hetzner Cloud's US West network zone. So we'll set that up here. Finally, we need to define the IP range. This will help us get a range of allocated IP addresses to use on our servers. Our defined network allows us to allocate IPs in the 10.0.0.0 subnet 16 range. So I'll take a slice of that and allocate addresses using the subnet address of 10.0.1.0 with a subnet mask of 24. This gives us 256 allocated IP addresses from 10.0.1.0 to 10.0.1.255. These resources will create a private network and give us a batch of IP addresses we can use for our server later. Again, let's make sure that we've set everything up correctly by going to our terminal and running Terraform plan. As we can see, Terraform is going to create a new private network and it's going to create our subnet. So this is looking correct. We can run Terraform apply to apply these changes to our account. A few seconds later, we'll see that our changes have been applied. Going back to the Hetzner Cloud console, if I go to the network sections, we'll see our private network along with the subnet ready to go. We've created a firewall and a private network with a subnet. So now it's time to put these to use on a server. Let's see how we can create one with Terraform. Once again, we'll go back to the Hetzner Cloud provider documentation and search for server. So we can find the hcloud server resource. This documentation has a lot of different examples on how to create new servers on your Hetzner Cloud account. Scanning down to the argument reference, we'll see a few required arguments like the name, the server type, and the image. We also have a couple of optional ones that we want to include, like the location, the SSH keys, and the firewall IDs. Going back to our configuration, we'll create one more resource block at the end of our Terraform configuration file with a resource type of hcloud server, and we'll identify it with airport gap. Let's start filling in all the arguments we want to use to spin up our server. The first argument we want to start with is the name, which I'll set up as airport gap. The next argument we'll set is the server type. There are a couple ways to get the value for the server type, like using Terraform data sources and filtering them. But for the purposes of this video, the easiest way to find the value to use here is to go to the server's overview page on the Hetzner Cloud documentation and find the server specs you want from the list. Each server type will have a name defined here. In this example, I want to spin up a server with the CPX21 server type, which is a server that uses 3 AMD vCPUs and 4 GB of RAM, which is enough for this demo. The value that goes in the server type is the name of our server that we want, but in lowercase letters. So in this case, CPX21 in lowercase. Next, we'll specify the location of the server. This value defines the data center location to spin up our server. Again, we could programmatically find this, but for simplicity, I'll get the value from the Hetzner Cloud documentations, this time in the location section. This page shows the current locations that Hetzner Cloud has available. Earlier in this video, we set up a private network for our server in the US West location. To use this private network, we'll need to place the server in the same location. So in this case, we'll need to spin up the server in the Hillsboro, Oregon location defined as HIL. So we'll set this value as the location. The final required argument for this resource is the image, which is the operating system image maintained by Hetzner to install on the new server. We can also find this information in the documentation under the operating system's standard images section. We have a few Linux distributions to choose from, like Debian and Arch. In this example, I'll use the latest available Ubuntu since it's one of the easiest distros to use for deploying apps with Kamal. The latest Ubuntu version that Hetzner Cloud has available is Ubuntu 22, so let's use that. For the value of the image argument, we'll set it as Ubuntu-22.04, using lowercase and a dash between the distro name and the version number. That takes care of the required arguments for creating a new server. While we can run Terraform Apply now to do that, we still have a couple of optional things to set up. First, we want to make sure that our server has our SSH key when it's created so we can have immediate access to it. We can do that by setting the SSH keys argument. This argument uses a list of SSH key IDs that we set up in our account. We already set up the SSH key earlier, so now we need to fetch the ID. We'll do that programmatically in Terraform using the provider's data source. In the Hetzner Cloud provider documentation, we'll have a section on different data sources, which is a way for Terraform to get information outside of our configuration. This provider has a lot of different data sources available, but the one we're interested in now is the hcloud SSH key. The examples here show a couple ways we can use this data source. We already have the name of the SSH key that we set up earlier on Hetzner Cloud, which is Airport Gap Demo. So we'll find our SSH key ID by name. Setting up a data source in Terraform is similar to setting up resources. We'll create a new data block, which I'll create at the beginning of the file, just before the resources. I'll set the type with hcloud SSH key, and set an identifier of airport gap SSH key. The argument we want to use in this block is the name, so we can search for our SSH key by name. So we set the name as the same name that we used to set up the key on the Hetzner Cloud account. Now that we have this set up in our configuration, we can use it as a reference to get the information we need, similar to how we got the private network ID earlier in this video. Let's go back to the server resource block. And in the SSH keys argument, we'll create a new list containing the ID returned by the data source, which is data.hcloud SSH key.airport gap SSH key. We also need the ID for this, so we'll append the ID identifier at the end of it. Notice that when referring to data sources in Terraform, it's slightly different than referring to managed resources. For a data source, we have to use the data as part of the identifier, where for resources, you just start with the resource type, as we did earlier. With this setup, the next time we run Terraform Plan or Terraform Apply, the Hetzner Cloud provider is going to first fetch the SSH key information from our account and then set it up when creating this resource. That way, we'll be able to log into the server directly without needing to do any additional configuration. Another setting we need to do for our server is to set up the firewall. We can do that using the firewall IDs argument. As the name suggests, it also accepts a list of IDs referring to the firewalls that we have in our project. Because we're using Terraform to manage our firewall for the server, we can use it as a reference. All we need to do is to create the list using the ID from the resource we set up earlier, which is hcloud firewall.webserver.nSSH, and the ID, which is ID. The last thing we need to do before creating the server using Terraform is to set up our private network, so the newly created server gets a private IP address immediately allocated to it. We can do this by using the network block inside of our resource. The network block requires the network ID argument. Since we're managing the private network with Terraform, we can get this ID by grabbing the reference from our resource, which is hcloud network airport gap private network .id. The network block also accepts additional arguments like an IP address, but will let Hetzner Cloud automatically assign one for us from our subnet. Now, there's one hidden gotcha here. When applying these changes to your infrastructure, Terraform is pretty good at inferring the order for which to create the defined resources. It doesn't run the configurations sequentially from top to bottom. Instead, it analyzes the configuration, and based on how we're referencing other resources, it will attempt to create the resources in the correct order. For example, in this resource block, we're referencing the firewall ID and the private network ID. Terraform will see this and do its best to get these resources created first before attempting to create our server. However, in some cases, this automatic analysis doesn't work as expected. Attaching the network to our server is one situation where this won't work. Here, Terraform will create the private network and then proceed with creating the server. However, the server also needs to have the private network subnet created before it attaches to this server. Since we're not referring to the subnet in this configuration, Terraform might attempt to create both resources at the same time, which can result in the server creation failing if the subnet isn't available at the time that the server is being created. So to handle these scenarios, Terraform provides the depends on argument, which lets us explicitly specify any dependencies needed by a resource when we're not referring to them inside of it. When creating a new server on Hetzner Cloud and attaching it to a private network, we need to make sure that the subnet is already created first. So let's add this to the configuration by creating a new list and setting the subnet resource as a dependency, which is the hcloud network subnet, which we called airport gap private network subnet. Now keep in mind that when setting an explicit dependency using the depends on argument, we'll need to use the resource type and the identifier without any IDs or anything else set up. With this, we now have our server setup completed. All that's left to do is to run Terraform plan to check that everything is set up correctly. As we did before, let's go back to the terminal and run Terraform plan to make sure everything is configured correctly. And it looks like we don't have any errors, so it looks like everything is ready to go. So let's go ahead and run Terraform apply to get this server up and running. After a short while, we should have a brand new cloud server spun up and ready to use. If I go back to the Hetzner Cloud console and then go to our server section, we can see the new server is up with all its information. To make sure everything is working correctly, let's SSH onto the server. I'll copy this public IP address and then go to the terminal, and I'll SSH as root onto the server. So it seems that our server was spun up correctly and our SSH key was placed correctly on the server. If this server were for a production environment and not for demonstration purposes, I would take some time now to begin securing this server by disallowing password logins through SSH, creating separate user accounts, and more. But since this is for a demo, it's out of the scope of this video. Just keep that in mind whenever you create new servers for your applications. So now we have a place to deploy our Rails application using Kamal. Let's start doing that by switching to the airport gap codebase and begin setting that up. Before we begin setting up Kamal in our Rails application, I just want to make a few notes. In the beginning of the video, I mentioned that one of the prerequisites for using Kamal is a web application that has a Docker file to containerize the application. As I showed earlier, the Airport Gap application already has a Docker file, so I won't be going through the process of creating a new one. Rails 7.1 and above generate a new Docker file by default for new applications, but you need to create your own if you're running an older Rails application. Another prerequisite you need in your application is a health check endpoint. Kamal needs to send a GET request to an endpoint to ensure that it's up and running during deployment and while active. By default, Kamal will ping the up endpoint in your application. Rails 7.1 and newer applications have the health check endpoint set up at this route. For older Rails applications, you need to set up your own. The Airport Gap application uses Rails 7.1, so we won't need to do anything else here. With these prerequisites out of the way, let's begin setting up Kamal. We'll start by installing Kamal, which is a gem. So we'll install it with gem install Kamal. When the gem is installed, we'll initialize our project to use Kamal with the Kamal init command. This command generates a few files. The main file we'll want is the config deploy.yaml file, which holds the settings Kamal needs to deploy your application. We'll come back to this file later. The next file it creates is a .env file. Kamal uses the .env library to read from this file and allow you to set up environment variables that will get injected into the Docker containers on deploy. This will help you set sensitive data without using plain text inside of your settings. Since this file contains sensitive data, you should make sure the .env file is in your ignored file list for your code repository. If you already use .env for your project and have a .env file, Kamal will skip creating it. Finally, the init command also creates some hooks inside of the .kamal directory in your application. These hooks are used to run commands at different points of the deployment lifecycle. We won't be using these in the video. Let's go back to the generated deploy YAML file. The default configuration contains plenty of commented out examples of the different settings you can use. It'll give you a better understanding on how to configure it to deploy your application. I'll go through most of these sections and explain the ones that we'll use for our scenario. The first setting we'll use is service, which is the name of our application. Kamal will use this to prefix the name of our Docker containers on deploy. We'll call our service Airport Gap. The next setting here is image. Here is where we define the name of our Docker image. When deploying an application with Kamal, it'll build the Docker image on our local system using this name, then push the image to a container registry, which we'll configure later. The image name depends on your container registry's requirements and naming conventions. In this example, I'll use GitHub's container registry, which uses the name of the GitHub account we'll use. In this case, Denmark, followed by the desired image name. We'll use Airport Gap for the image name. Next, we have our servers, where we plan to deploy our web application. The example configuration shows a single host, but we can set a list of servers or split them into roles, which lets us individually configure different groups. The Airport Gap application has its main Rails web application, but it also uses Sidekick to run asynchronous jobs. Sidekick runs as a separate process, even though it's on the same server. So we'll split out the server configuration into two roles, a web role and a worker role. I'll need the public IP address for the server I just created. So I'll go back to the Hetzner Cloud console, grab the IP address, and paste it under the host key. I only have one server, so I'll use the same host for both roles. One additional thing we'll need to set up here is the command we want each role to run when deploying the application. The Docker container will run the defined command specified in the cmd instruction for the Docker file. As we see here, the Docker container will run the Rails server process. For the web role, this is exactly what we need. But for the worker role, we don't want to run the Rails server. Instead, we want to run Sidekick so it can process our asynchronous jobs. We can override that in the configuration with the command setting for this role. In this case, we'll run bundle exec sidekick and set the queues that we want to process for our app. In this case, it'll be the default queue and a mailers queue. Now, before moving on, I wanted to explain how Kamal handles these roles. If you're using different roles, it's important to have at least the web role set up. Under the hood, Kamal uses a reverse proxy called traffic. Kamal will set up traffic to expose port 80 on the host, which will route it to the Docker container. It won't do that for any other role, which is fine since we don't need to access the Sidekick process outside of the server. Another note I wanted to mention is that if you deploy your Rails application to multiple web hosts, you'll be able to access the application on each host individually. However, if you want to distribute traffic between them through a single domain name, you'll need a load balancer in front of your host. Kamal won't set this up for you, so it's an additional piece of infrastructure you'll have to manage on your own. Going back to our configuration, we're now at the registry settings. Here is where you'll define which container registry you'll use for pushing your Docker images from your local system and where the servers will pull them from during development. The default container registry Kamal uses is Docker Hub. However, we want to use GitHub's container registry instead, so we set the server to ghcr.io, which is GitHub's container registry. Since we need to write to the container registry, we'll need to set up authentication with a username and password. We can set up the username in plain text. For GitHub's container registry, the username is the same name as your GitHub user or organization. In my case, it'll be Denmark. For the password, GitHub's container registry requires an access token when publishing images. I already have an access token for this, but I don't want to set this sensitive piece of information here. Instead, we'll follow the example mentioned here and use the Kamal registry password environment variable. We'll need to set up the value of this environment variable in the .env file, so let's do that. Going back to the deploy YAML file, the following section is the .env section. This lets us specify environment variables that'll get injected into the Docker containers running on the servers we specified earlier. This section is vital for setting up any sensitive details like database passwords and API keys. It also helps with configuration. The env section is split into two groups, clear and secret. The environment variables set under clear use key value pairs for non-sensitive configuration settings that can be set in plain text. The secret section will hold a list of environment variable names for specifying sensitive data you don't want exposed in plain text. The values for these environment variables will be taken from the .env file. I've set up a few environment variables that the Airport Gap application requires to work properly, and set up any sensitive values in my .env file. The ones in clear are basic configuration settings that don't need to be secured, like the Rails environment or the application host. The environment variables under secret should not be exposed here, like the Rails master key or the SMTP settings for sending emails. One thing to note here is that the values of the secret environment variables will be in a file stored inside of the servers that Kamal deploys to, and they'll be injected as plain text into the Docker container at runtime. So anyone with access to your server or running the Docker containers will be able to access this information. If you need stricter security around your secrets, you need to look into a separate secrets manager like HashiCorp Vault or AWS Secrets Manager. The following section is to set up the SSH settings for logging into your servers. The example here shows using SSH with a user other than root, which is Kamal's default. For our demonstration, we'll use the root user so we can remove the setting. Next up is the builder section. In this section, we can set up the configuration used to build the Docker image for our application. There are a lot of settings here that you can use depending on your needs. Kamal's documentation has plenty of examples, but we'll keep it very simple for our situation. By default, Kamal builds multi-architecture Docker images for your application. This is helpful if you're developing your app and deploying it on different architectures. For example, you're using an Apple MacBook or Mac Mini that uses Apple Silicon, which is the ARM architecture, but deploying the application to a server that uses an Intel or AMD chip, which is a different architecture. Kamal will first build images for both of those environments and use what it needs accordingly. However, creating Docker images for multiple architectures is really slow since it needs to emulate the architecture while building. I'm using the same system architecture both for development and deployment environments, so I can bypass this by setting the multi-arch value to false. This will speed up my deployments quite a bit because it doesn't have to build multiple Docker images for different architectures. I'm not going to use any of the other settings, so I can remove them. The final section we'll configure for this demo is the accessories section. This section handles the additional services needed for the application to run, like a database server. Kamal handles accessories separately during deployments, since you typically don't need to redeploy or restart these services every time you update your application. Each accessory is defined with Docker images, either publicly available or from the private registry set up earlier in this video. The Airport Gap application needs two accessories, a Postgres database server and a Redis server. Let's start setting these up by clearing all the existing configuration before it. First, we need to specify a name for each. For the database, I'll call it DB, and for Redis, I'll call it Redis. Each of these accessories requires a Docker image. I'll grab them from the public Docker Hub registry and use the latest stable versions as their respective tags. So for Postgres, the image will be Postgres, and the latest tag as of this recording is 16.2. And for Redis, the image will be the Redis image version 7.2. Each accessory requires the host where we'll deploy them. We'll host everything in a single server, so we can use the same IP address that we've been using so far. So we'll just grab the IP address from the host and then set the host for each of these servers. We'll also need to specify the ports to expose for each accessory and map them if necessary. We'll just expose the ports used for each service. So for Postgres, the port will be 5432, and for Redis, the port will be 6379. Now, we can keep this as it is, but an important note to make that I mentioned earlier is that Kamal will expose these services on these ports through the host IP address. That means that if your server allows public access to these ports, anyone could access them. So it's important to secure these services with passwords or secure them using a firewall. We already have a firewall on our server that doesn't allow access to these ports externally, so we're safe on that regard. But what if somebody accidentally opens up these ports on the firewall and we don't notice it? To make sure any future changes don't create a security hole, we can put the private network we created to use here. Our server has a private IP address assigned by it that's not exposed to the public. We can take this IP address and append it to our port configuration in the Kamal configuration. That way, the service is only exposed within the internal private network, keeping it secure from the outside world. So I'll just copy this IP address and then append it to the port for each one. This way, Kamal knows that these services will come from this particular IP address, which is our private network that is not accessible to the outside world. Now, since the accessories that we configured here are Docker containers, that means they're ephemeral, meaning that any data they contain will be lost if the Docker container or the server goes down or is shut off. So since we don't want our database to disappear with all the data if the host goes down, we'll need to store that data somewhere. In that case, we can use the directory setting, which will create a directory on the host and mount it as a volume on the Docker container. That way we can keep the data on the service even if it goes down. Both the Postgres and Redis Docker images have details on their readmes that tell you where this data is located on the container. So we'll set it up here. For both accessories, we'll create a volume called data and mount it to the container's internal directory where each service stores its data. The last thing we need to do here is configure each service through environment variables. We won't need to do any additional configuration with Redis, but we do want to set up a few things on the Postgres service. We can set up environment variables for these specific accessories under the env setting. This works the same way as setting up environment variables for our application, which we did earlier in the video. We can set up clear or secret environment variables as needed. For the database, we want to create 3 secret environment variables. We'll set up the Postgres DB environment variable, which lets us name the database we want to use. We'll also set up the Postgres user, which lets us set the database user, and we'll set up the Postgres password to include a secure password. Remember to set the values for these variables up in the .env file. All the settings needed for the accessories will depend on the Docker image you use, so please make sure to read the documentation for any image you use as a service to understand which environment variables or volume mounts you need to use to configure them. This wraps up our initial Kamal configuration. We have a fully configured deployment file and all the necessary environment variables defined in .env. One thing I forgot to mention here is that when we're setting an IP address to the port so that we can limit the scope of this port and not have it open to the public, is that we need to also set up the port where we want to expose this on the server. So we kind of have to duplicate this here. So this kind of means that Docker will see it as this port from the private network will be exposed to this port on the actual server. So we kind of have to duplicate this here. Just a note to remind yourself if you're limiting this to a private network. All that's left to do is to perform our first deployment. The first time we deploy an application using Kamal, we use the Kamal setup command. This command performs the initial setup on our remote servers before setting up the application. First, it'll log in to our defined servers through SSH using your public key as set in the configuration file. When logging in as root, it'll check that Docker and curl are installed, and if they're not, it'll set them up for you. It's important to note that this step only happens if you're logging into the server as the root user. You'll need to manually install Docker and curl if you want to use another user account on the remote servers. After making sure Docker is set up, Kamal will push the environment variables and values defined in .env to the remote servers. Then it'll build the Docker image on your local system based on your application's Docker file. When the image finishes building, it logs into the container registry and pushes the image. Next, it'll log into the container registry on the remote servers to pull in that newly built image and run it in a container. Kamal will then set up traffic on the web host defined in our configuration and open traffic up to port 80. All the accessories will also get set up during this process. Finally, Kamal will run health checks to ensure that the application is up and running. So let's run this command and see how it goes. If everything goes well and you don't see any error messages, you can now access your application on your web servers by going to your IP address. So if we open a new web browser, we put in our IP address. If everything went well, we'll see our application up and running. So when Kamal works properly, the entire process just takes less than 5 minutes to set up your server, set up Docker, set up the containers, and get everything up and running. Once you have your application deployed using Kamal, you can continue managing it using various commands from the gem. Here are some of the more important commands you'll find yourself using frequently. The command you'll likely use the most is Kamal deploy. This command bundles up the latest updates for your application using Docker, pushing the new image to the registry and use it to replace the currently running containers on the remote servers. One thing to note is that this only updates the containers defined under servers in your configuration. So in our case, that means the web server and the worker process. It won't touch any other containers that are running in the system, like traffic or any of the accessories you may have defined. Another command you'll likely need to use frequently is the Kamal env push command. So anytime you update your .env file, you'll need to push those changes to the remote servers using this command. Remember that you'll need to run the command before deploying your application with Kamal deploy. Anytime you modify your environment variables, you need to do this because otherwise the values won't be present on the remote servers. Kamal deploy does not push your environment variables at the same time. So Kamal won't be able to inject them to the new containers, and you might find your application not working properly after that. If you find that you accidentally deployed a buggy version of your app, you can quickly revert to the previous running containers using Kamal rollback. So by default, Kamal keeps old versions of your application containers on the remote servers, pruning any containers older than 3 days anytime you run Kamal deploy. You can find a list of these containers running Kamal app containers. Here, you can find the older deployed version and use the image tag to roll back that container. For example, we see the last deploy we made for our web server before the current running one is this particular one. So if we take the tag for this and pass it to the Kamal rollback command, Kamal will revert back to that version and restart the application for us. Finally, the last command you'll likely find yourself using frequently is the Kamal app exec command. You can execute commands on the application containers using this command and appending a command enclosed in single quotes to run on the remote servers. So for example, we'll check the version of Ruby on the server. So we see that this command actually ran twice. It's because if you're deploying your application to multiple servers or multiple roles like we did with the web and the worker role, the Kamal app exec command will run on all those servers and roles, which you probably don't want to do. You can filter which servers you want to execute the command on using flags like roles and specify which role you want to use to run this command. You could also set the primary flag so you can make sure that it only runs on the first host. So if you have a role with multiple IP addresses to deploy the application to, this will run it only on the first one. So as you can see here, we're only running it on one host this time. You can also run interactive commands by passing in the interactive flag. This is useful for running commands like the Rails console. Kamal has many other commands to help you manage your applications and the servers running them. I encourage you to check out the Kamal documentation for a lot more details. Services like Heroku and Render are excellent for your Ruby on Rails applications, but it's nice to have alternatives like Kamal that let you choose where to deploy them. Using Kamal frees you from the constraints that appear on those platforms as your apps grow. However, that's not to say that every Rails team should immediately switch their deployment methods to Kamal. Kamal still has a few rough edges to polish, like requiring a container registry and being difficult to debug when something goes wrong. But the team at 37 Signals continues to make improvements to the tool, and I have no doubt that in the coming years, Kamal will become the preferred way of deploying Ruby on Rails applications. If you found this video helpful, consider subscribing to this channel for more tips on helping Rails developers ship their code confidently, from development to deployment. You can also check out my website for more in-depth articles covering Rails, testing, DevOps, and other software engineering topics. Thanks for watching, and I'll see you in the next video.